Induced voltage in communication cables can stem from several factors. Electromagnetic induction, proximity to high-power electrical lines or transformers can induce voltage in nearby cables. Crosstalk can occur when parallel communication cables running close together can crosstalk with each other, causing induced voltage. Ground loops. Improper grounding or bonding can create ground loops, which allow current to flow in the communication cables, resulting in induced voltage. To address this, firstly, identify the source of the induced voltage. Use a voltage meter to check the induced voltage on different sections of the communication cables. Determine the distance and proximity to high-power electrical lines or transformers. Inspect parallel communication cables for crosstalk. Secondly, consider electromagnetic shielding. Use shielded communication cables with a metallic braid or foil wrap to reduce electromagnetic interference. Ensure proper grounding of the shield. Thirdly, focus on grounding and bonding. Bond the steel inner jacket of the communication cable at both ends of the run, as well as at any intermediate pull boxes. Bond all metallic conduits together into the service panel ground. Consider using insulated conduit bushings to isolate the communication cables from the conduit. Fourthly, think about isolation transformers. Install isolation transformers at the feed end of the communication cables to isolate them from the electrical power system. This will block any induced voltage from entering the communication cables. Fifthly, explore balanced cabling. Use twisted pair cables or balanced cables that minimize crosstalk by cancelling out opposing induced voltages. Sixthly, optimize cable routing. Route communication cables away from high-power electrical lines and transformers. Keep parallel communication cables physically separated to reduce crosstalk. Seventhly, implement testing and maintenance. Regularly test the communication cables for induced voltage and ground loops. Perform periodic bonding and grounding inspections to ensure proper connectivity. When measuring voltage on the jacket to the service neutral and experiencing arcs upon disconnection, it indicates a potential difference in current flow likely due to the induced voltage issue. Here's a more detailed explanation and approach given the specifics. The fact that you're measuring between 10 volts and 20 volts on the jacket relative to the service neutral, coupled with the arcing when disconnecting the bond, strongly suggests circulating currents within the communication cable shield or jacket. Given the configuration, where many cable runs are over 5,000 feet and the conduits are not bonded together, you're likely dealing with a ground loop issue exacerbated by electromagnetic induction from the nearby power lines. The standard practice of bonding the steel inner jacket at only one end is intended to prevent ground loops, but in your case, it seems to be inadequate or even contributing to the problem. Here's a breakdown of steps to diagnose and mitigate the issue. Firstly, verify grounding system integrity. Ensure that the service panel's grounding system is robust and compliant with NEC 2014. Check the grounding electrode conductor size and connections. Make sure there are no loose connections or corrosion. Secondly, implement multi-point bonding. Change the bonding strategy to include bonding at both ends of the communication cable runs and at intermediate pull boxes. This creates a more uniform ground reference along the entire cable length. Use appropriately sized bonding conductors and ensure they are securely connected to the steel inner jacket and the grounding system. Thirdly, bond conduits. Bond all metallic conduits together. Use grounding bushings and bonding jumpers to ensure electrical continuity between each conduit section and to the service panel ground. This provides a low impedance path for fault currents and helps equalize the ground potential along the cable run. Fourthly, isolate conduit bushings. As previously stated, use insulated conduit bushings. This helps isolate the communication cables from the conduit, preventing unwanted current flow through the cable jacket. Fifthly, consider shielded cable. If feasible, replace the existing cables with shielded communication cables. Ensure the shield is properly grounded at multiple points along the run. Sixthly, measure ground currents. Use a clamp meter to measure the current flowing in the bonding conductors and cable jackets. This can help identify the sources and paths of circulating currents. Seventhly, install isolation transformers. At the feed end, install isolation transformers to block induced voltage from entering the communication cables. Eighthly, test for voltage imbalances. Check for voltage imbalances on the power distribution system. Unbalanced loads can contribute to neutral currents, which can induce voltage in nearby cables. Ninthly, review cable routing. Ensure the communication cables are routed as far away as possible from high-power electrical lines and transformers. Maintain physical separation between parallel communication cables to minimize crosstalk. Tenthly, surge protection. Install surge protectors or transient voltage suppressors at both ends of the communication cables to protect communication equipment from voltage spikes. 11thly, document everything. Keep detailed records of all tests performed, measurements taken, and mitigation measures implemented. This documentation will be valuable for future troubleshooting and maintenance. Additional considerations include consulting with a qualified electrical engineer, especially one experienced in grounding and bonding practices for communication systems. Also, because arcing has occurred, prioritize safety. Wear appropriate personal protective equipment when working with these cables and grounding systems. Verify that all power is shut off to the circuits being tested before making any modifications to the grounding or bonding system. Remember, proper grounding and bonding are crucial for safety and performance. The NEC 2014 provides detailed guidelines on grounding and bonding requirements, which should be followed closely to ensure a safe and effective installation. Consider using a ground fault circuit interrupter, known as a GFCI, to protect equipment and personnel from electrical shock. Also, consider an equipment grounding conductor, known as EGC, which is required by the NEC 2014. Additional NEC references, such as Articles 250.92 and 250.96, detail the grounding and bonding requirements for services and metal enclosures. Regarding bonding requirements, all metal enclosures containing service conductors must be bonded, and with the metal enclosure is likely to become energized, it must be bonded to an equipment grounding conductor as outlined in NEC 250.92. Metallic conduits must be made electrically continuous by bonding, as per NEC 250.96, and that bonding should be sufficient to handle any fault currents that may occur. It's also important to select appropriate bonding methods such as bonding jumpers and grounding bushings to ensure reliable and low impedance connections. By following these recommendations, you should be able to significantly reduce or eliminate the induced voltage and noise on your communication cables, improving the performance and reliability while also enhancing safety. Keep in mind that addressing induced voltage issues often requires a systematic approach, combining careful measurement, thoughtful design, and diligent implementation of grounding and bonding practices.